Thinking like a quantum computer. Quantum computing sounds mysterious because it doesn't behave the way we expect computers or reality to behave. But this lesson isn't about complicated physics. It's about learning a new way to think about information. At the smallest scales, the world doesn't follow the rules we're used to, and quantum computing is built on that difference. From certainty to probability. Classical computers are based on certainty. A bit is always 0 or 1. There's no in-between. Every step follows a predictable path. Quantum systems are different because they reflect how reality behaves at the microscopic level. Instead of certainty, they work with probability. They don't always tell you exactly what will happen, they tell you what is most likely. This is a major shift. Instead of following one path step by step, quantum systems consider many outcomes at once, then use probability to guide them toward the best answer. That's the foundation of quantum thinking. Superposition. One of the most important ideas is superposition. A quantum bit or qubit can exist as 0 or 1, or a combination of both at the same time. A helpful analogy: a classical bit is like a light switch, on or off. A qubit is like a dimmer switch, partially on and off at the same time. Another way to imagine it: a classical bit is like a coin lying flat, heads or tails. A qubit is like a spinning coin, representing both possibilities at once. This doesn't mean the qubit is undecided. It holds multiple possibilities. But there's an important catch. The moment you measure a qubit, it collapses into a definite value, either 0 or 1. Before measurement, it exists in probabilities. This allows quantum computers to explore many possibilities at once, instead of checking them one by one. Entanglement. The second key idea is entanglement. When qubits become entangled, their states become linked, no matter how far apart they are. If you measure one qubit, you instantly gain information about the other. Imagine two perfectly synchronized coins. Even if separated across the world, flipping one reveals the other. This connection does not exist in classical systems. Entanglement lets quantum computers coordinate information across multiple qubits, enabling complex problem solving. But qubits are fragile. Heat, radiation, or vibrations can break entanglement. This is called decoherence, a major obstacle to reliable quantum computers. What quantum computers are and are not good at. Quantum computers are not simply faster computers. They are specialized tools for certain problems. They excel at simulating molecules, solving optimization problems, improving AI, and analyzing large numbers in encryption. Companies like IBM, Google, and Microsoft are developing them, often accessed through the cloud. However, they struggle with everyday tasks. They are not ideal for browsing, simple calculations, or running apps and games. Classical computers remain faster, cheaper, and more reliable for daily use. Here's the reality check. Quantum computing is powerful but still developing. Current systems face challenges: high error rates, extreme code requirements, and difficulty scaling stable systems. Experts believe large-scale, fault-tolerant machines may not arrive until around 2030 or later. There is also a talent gap, with too few trained experts. While the potential is huge, it is important not to oversell what quantum computing can do today. In practice, progress is steady but incremental, with researchers improving error correction, hardware design, and software tools. Collaboration between academia, industry, and governments is accelerating innovation and expanding access to quantum resources. Education and workforce development will be essential to close the gap and turn theory into practical applications in the coming decade for many industries. Superposition and entanglement don't make quantum computers magical. They make them different. Quantum computing works not because it breaks the rules of reality, but because it follows the rules that reality already uses at its smallest scales. Understanding these ideas isn't about memorizing formulas. It's about being open to a new way of thinking. A world where certainty is replaced by probability, and where solving problems means exploring many possibilities at once.